Good morning. I think maybe we can start now the morning session. I'm sorry, I had some technical problems with my Teams, but I hope somehow to survive. So today's first speaker will be Daniela Oriti, who will tell us about the universe's quantum gravity condensate. So please, maybe start. Thank you very much.
Yes, so thanks for the introduction and for the invitation to the organizers. So the first thing I want to mention is the variety of quantum gravity approaches. And even more, I want to stress the many mutual relations among them. This is because I'm going to discuss one particular approach, which is, however, strictly related to a bunch of others. In particular, I will mention the relation to what Jan has been discussing a few days ago. And in fact, I will take the perspective for introducing this approach of the simplicial gravity path integrals. So the approach is called group field theories or tensorial group field theories, depending on which aspect you want to emphasize. So the first thing I'm going to say is a bit of a plan of what is going to follow. So I want you to keep in mind the general idea of a path integral for simplicial geometries, so a lattice gravity path integral. The picture, the general idea is the one in the formula, which of course is not a precise formula, is the idea of writing down a path integral for defined by sum over geometries in which the space-time manifold has been replaced by some lattice, some triangulation, for example, of some topology, and the Einstein-Hilbert action that would enter the continuum path integral is instead replaced by some discretized gravitational action, a discretized version of the Einstein-Hilbert action. What I'm going to show is four things. So these are the four main messages. One, the starting point is that this discrete lattice path integral for gravity can be defined in terms of group theoretic variables and ingredients. The second is the moment you do that, you can also embed it in a broader framework that is a quantum field theory on some auxiliary group manifold, and that is what is called group field theory. The third point and the fourth points are the fact that thanks to this embedding into a quantum field theory formalism, you can tackle a number of issues concerning, in particular, the extraction of continuum physics from the discretized path integral using powerful field theoretic methods. And I'm going to discuss in particular how you can take advantage of this formulation to extract effective continuum cosmological dynamics from the hydrodynamics of the broader field theory. So this is the plan. I start with the first point. I show you how to formulate a discrete quantum gravity path integral in group theoretic variables. I focus first just on the three-dimensional example to give some more concrete detail, and then I simply point to how the idea can be generalized to arbitrary dimensions, in particular to 4 dimensions. Now, let's start with the simplest building block of a 2-dimensional space, a triangle. The starting point is that we know out of just vector geometry that we can describe the geometry of a classical triangle in R3 using 3 edge vectors that imposing that they close, and there's nothing else. So these 3 vectors in R3 with a constraint that tells that they close is enough to describe the geometry of the triangle. We can think of the R3 space as the actual SU2 Lie algebra, And we can think of this intrinsic geometry as part of a classical phase space, which includes also extrinsic data, being instead group elements, which you can think as a discrete connection associated to the same links. So we can say that the phase space for a single triangle in discretized three-dimensional gravity is given by the cotangent bundle of SU2, well, 3 copies of it, 1 for each edge of the triangle. The point is that these variables are discretized three-dimensional variables if you come from a continuum theory that is just the first order gravitational action, the one that is shown here. So in terms of a triad, one form, and the curvature of a connection, one form. You can think of the Lie algebra variable, these 3 vectors associated to the triangle, as the discretization of the triad along the edges. And you can think of the group elements which form the conjugate variables, which constitute the conjugate variables, to parallel transports of the connection along paths dual to the 3 edges. Given that phase space, you can quantize and obtain the Hilbert space for a triangle, and you can give it 3 representations. Let me just mention one. Well, let me mention 2 actually. One is if you use the group elements as your basic variables, you can give that Hilbert space as the tensor product of an L2 space over SU2, over the group. And dually, you can also give it as an L2 space over the algebra with some additional technical ingredients. If you take functions on the group and you expand in representations of SU2, then you get the same states labeled by representations of SU2, which are basically spins. Now, the point of this that you have to keep is simply that you can quantize the phase space associated to a triangle and describe in group theoretic variables to obtain a Hilbert space given by functions on the group and any possible Fourier transformed representation. The next point is that starting from the same continuum action and discretizing with the same type of continuum variables, you obtain the action written here, which involves the Lie algebra elements that represent the edge vectors for a triangle, and you do that for all the triangles in your triangulation. And the curvature of the connection discretized in terms of group elements. So this is the discretized counterpart of this continuum 3D gravity action. Using this discretized action for 3-dimensional gravity, you can write down the path integral by taking the exponential of it and then integrating with the Lebesgue measure over all the algebra elements associated to all the edges of your triangulation and all the group elements that represent the connection. So this is a discrete gravity path integral with the natural discretized version of this first order 3-dimensional action for gravity. You can find several equivalent representation of the same path integral. I mentioned only one. If you expand everything again in representations of SU2, of the group you're using, you obtain what is called a spin-form model, which is which can be seen as a covariant version of the dynamics of loop quantum gravity. So this is the first point. The only other thing I will say quickly is that the same construction can be generalized in 4 dimensions and in fact in higher dimensions. I spare you the details. The general steps are the same. So you consider the building blocks in 3 dimensions, the building blocks for the states, so for the 2-dimensional slices were triangles. In 4 dimensions, the building blocks for states, that is for 3-dimensional slices, of your path integral will be tetrahedra. So you quantize, you first describe the classical phase space of tetrahedra in terms of group theoretic variables, and you have to use the Lorentz group as your relevant group manifold and algebra. And you have to impose constraints which restrict your Lie algebra and group theory data and group variables to give them a geometric meaning, so that they can indeed be understood as describing the geometry of a single tetrahedron. These constraints, in fact, reduce the old description to SU2 again. And then you can quantize, obtaining as a Hilbert space in one representation, the L2 space over several copies of a group, plus additional constraints. And then you can construct, similarly to the three-dimensional case, a discretized path integral associated to a four-dimensional lattice now, to which you assign the same type of Lie algebra or group elements, so group theoretic data. Again, I'm sparing you the details, they're not crucial here. The point is that the procedure that I've shown with a little bit more details in the three-dimensional case can be generalized straightforwardly, but with, of course, with some technical care to the four-dimensional case. So let's take the endpoint of this discussion so far. So we have some discretized version of a gravitational theory on a given lattice in 3, 4, or higher dimensions in terms of a lattice to which you assign group theoretic data. But of course, if you restrict your description to a finite lattice, you have a finite number of variables. That's not enough to define the full continuum gravitational path integrals. One way to try to really achieve a definition of the full continuum path integral, but in terms of such discrete structures, is, as you've seen in the talk by Jan a few days ago, to sum over the triangulations. You know that if you're summing over all triangulations weighted by some discrete gravity path integral, you are in fact certainly encoding enough data, enough degrees of freedom to capture the relevant information encoded in continuum geometries. What I'm going to do here, indeed, is to give you, to show you how you can give a full definition of this path integral, of the discrete path integral, at least formally at the beginning, that has a sum over all lattices, in which each lattice is weighted by a discrete path integral for gravity on that given lattice. In fact, as you see, I'm attaching additional data to the lattice which have an interpretation of discrete geometry. And the fact is that if I fix all these additional data and I keep only the sum over triangulations, so I only keep the combinatorial aspects of the construction, by interpreting the corresponding triangulations as equilateral, then I in fact reproduce the setting of dynamical triangulations. So let's move one step further. The moment you have this type of formal definition of a candidate path integral for continuum quantum gravity in terms of a sum over triangulations, each weighted by a discretized path integral, of course, the first problem is which triangulations you include, you summing over topologies, how you control this sum, can you numerically evaluate, can you analytically control the sum, and how do you compute continuum observables. So the old problem is to extract an effective continuum description. The point that I want to emphasize is that defining the continuum path integral becomes equivalent to computing this sum over discrete structures. Again, in the same spirit as dynamical triangulations, just with an enriched set of data. What I'm going to show now is how you can actually obtain this sum over triangulations weighted by the same discrete path integral I've introduced earlier from some auxiliary, so to speak, group field theory. So we take the starting point, the group theoretic starting point we had at the beginning of our description of discrete geometry. We define a field theory over a group manifold so that the corresponding phase space for the classical phase space for the quanta of the field theory is the same phase space we were using earlier to describe little building blocks of triangulations. So for a triangle, we had the cotangent bundle of 3 copies over 3 copies of SU2 in the Euclidean case. We take this to be the classical phase space for each single quantum of this field theory. So in practice, we define a field over 3 copies of SU2 for that type of model. In the 4-dimensional case, it will be 4 copies of the Lorentz group, given that the classical phase space was the cotangent bundle over 4 copies of SO4 or SO31, sorry, the Lorentz group. That is, at the quantum level, we are taking the same single particle Hilbert space that we had earlier, given by an L2 space over the group, over several copies of the group, and constructing the corresponding Fock space to have a field theoretic description, a second quantized description of simplicial geometry. Then, depending on the model and depending on the dimension you're in, you have to put additional constraints on the fields representing the geometricity constraints that allow you to use the group theoretic data to describe simplicial geometry in 3, 4, and higher dimensions. So you have a description in which you start with some Fock vacuum in which there's no structure. Then in the 4-dimensional case, you have creation and annihilation operators, and the creation operators are going to create quanta, which you can understand as tetrahedra labeled by group elements. And a generic quantum state, so created by some arbitrary insertions of creation operators, is going to be some collection of tetrahedra. And among the states you can create are those that you can interpret as corresponding to glued tetrahedra to form extended 3-dimensional triangulations. Then you choose a dynamics, and the criterion for choosing a dynamics is that the interactions of your fundamental building blocks of 3-dimensional space should be such that they constitute elementary building blocks for 4-dimensional triangulations. So the interaction kernel in the action is chosen so that it represents the interaction of 5 tetrahedra, for example, in the simplicial setting, to form a 4-simplex, the building block of a 4-dimensional triangulation. So that's how you choose the combinatorics of arguments in the interaction. It represents the gluing of 5 tetrahedra across common triangles to form a 4-simplex. And this is the combinatorics. You have 5 fields, each representing a tetrahedron, with 4 arguments each representing a triangle on the boundary of a tetrahedron, and they have to be glued together to form a 4-simplex. So this, of course, is a special example of the general formalism. It built so to represent simplicial 4-dimensional structure as interaction processes of 3-dimensional building blocks, the tetrahedra. The whole construction, the whole formalism is built so that you can write down formally the partition function of the field theory with the type of action that I just mentioned. And when you expand perturbatively into the coupling constants labeling your interactions, you expand perturbatively in Feynman diagrams, in elementary processes, interaction processes of your building blocks. These Feynman diagrams, by construction, are going to be dual to lattices. So to triangulations in the example I mentioned earlier of the appropriate dimension. The next thing to emphasize is that because the triangulations are generated through a Feynman expansion in which you just glue things together, then the triangulations you're going to generate can be of any topology a priori. It's part of the model building and then part of the dealing with the theory to control the corresponding sum over topologies. The next thing to emphasize is that when you write down the Feynman amplitudes corresponding to each triangulation, what you find is that for models which are constructed like this, the amplitudes are indeed exactly the lattice gravity path integrals I introduced earlier. So you have a combination of a dynamical triangulations idea in which you sum over all triangulations with the simplicial gravity path integral for each triangulation. I just show you the example. Again, for the three-dimensional case that I describe in a little bit more details, this particular action for the group field theory, based on fields defined on SU2, and with an additional condition on the field, as a result that when you write down the Feynman diagrams and compute the Feynman amplitudes of the theory, the amplitudes look like exactly the discrete first-order path integral for 3D gravity that I had introduced independently earlier. So the path integral comes out as a Feynman amplitude of the field theory. And again, this is a general fact about this type of field theories. And again, the construction can be extended to the four-dimensional case. Last of this introductory part, what I want to emphasize is that just like I mentioned at the level of the individual path integral, the moment you fix all the group theoretic data to describe an equilateral triangulation, you're left with a dynamical triangulations setup in which you define the full theory by a sum over triangulations, which is purely combinatorial. The same can be realized at this group field theory level. You can start with the group field theory I just gave you. You restrict all the group theoretic data in such a way that you basically replace the Lie group with some finite set. Your field becomes a tensor over this finite set. The action becomes purely in terms of contractions of such tensors over the finite set. And the Feynman amplitudes become purely combinatorial, and you indeed reproduce exactly the setting of dynamical triangulations in the Euclidean context, which is what this model refers to. Okay. So we are again looking at a particular way of defining the full continuum gravitational path integral, a strategy to define the full gravitational path integral through a simplicial path integral embedded in a field theoretic setting. And here, defining the full simplicial path integral, so really the full continuum theory, doing the full sum over triangulations weighted, as I said, by a discrete path integral for each triangulation, amounts to defining the underlying group field theory path integral for the model you are interested in. So the issues are in many ways the same. Of course, you have to tell me which model you want to consider and why you think that that is the correct definition of the path integral. You may want to restrict the triangulation generated as Feynman diagrams, but then most important, you want to control this perturbative sum, this particular expansion of the full partition function of the group field theory, study the continuum limit, continuum phases, critical behavior, and so on. But most importantly, you want to be able to extract effective continuum physics and show that it has to do with the continuum gravitational dynamics. So this is what I'm going to discuss in the following. First of all, I just mentioned that thanks to this quantum field theory embedding, the technical problem of defining the continuum limit can be translated in quantum field theoretic terms in the language of group field theory, and it becomes the problem of establishing the renormalization group flow of the group field theory model you have chosen. So you translate and you change perspective from the discrete path integral that appears in the perturbative expansion of such field theory to the problem of study the critical behavior and renormalization group flow of the underlying field theory. This is the problem of group field theory renormalization. You can take advantage of the field theoretic structure to set up the whole renormalization group scheme. And the only thing I'm going to say is that there are a lot of results both at the perturbative level, showing that indeed this type of field theories can be well defined, fully renormalizable as quantum field theories. And also there are a lot of results at the non-perturbative level, meaning that we can indeed control the sum established in critical behavior for a number of models. And that we are building a lot of expertise in dealing with this type of exotic field theories. Instead, I'm going to shift to the more physical aspect of the problem. How do you extract continuum gravitational physics out of the same field theory, out of the formal definition of the field theory? In particular, I will focus on cosmology, given that it is one of the main themes of the workshop. So let's ask ourselves first a general question. If I'm presented with this type of candidate definition of quantum gravity, and that is a candidate definition of the full lattice gravity path integral, including its continuum limit, it should be clear that continuum physics has to be looked for in the coarse-grained description of the underlying quantum gravity data. So it should be the result of summing over lattice data. From the point of view of the group field theory, it should be non-perturbative quantum gravity physics. So it should really be the result of resumming the lattices that arise in the perturbative expansion. And third, it should be understood as the result of collective quantum dynamics of the fundamental discrete degrees of freedom. So it's continuum physics, usual space-time notions and geometry are collective entities from the point of view of the degrees of freedom that define the theory. So ideally, if this is your task, and you are given the field theory, that means that you should compute the full free energy and its derivatives, or the full quantum effective action of the underlying group field theory model. Is that the thing that will allow you to compute the full continuum geometric observables and their quantum dynamics? Of course, this amounts to resumming exactly the whole triangulations weighted by a complicated path integral. So this is really too complicated. And you need approximations of all sorts. And again, the field theoretic embedding of the simplicial gravity path integral gives you an advantage, which is that it suggests and provides a number of tools and strategies for approximating the full sum. The simplest one would be, if you're given the field theory definition, simply to use mean field theory, which is basically the saddle point evaluation of the path integral whose perturbative sum gives you the sum over triangulations and the discrete gravity structures. So what I'm going to do in the following is to look for the simplest continuum of gravitational dynamics in the simplest hydrodynamic approximation of the full quantum gravity theory. And if you want, the underlying rationale here is that you can see cosmology not so much as the dynamics of spatially homogeneous geometry in the sense of symmetry reduction that would lead upon quantization to quantum cosmology, which of course can give a lot of indications of what can happen to cosmology in a quantum setting within quantum gravity. But it's more difficult to derive, it still needs to be derived from the full quantum gravity theory. But it stems from a view on cosmology as being itself the result of coarse-graining up to homogeneous global quantities only, the underlying gravitational degrees of freedom. So you see cosmology as the effective dynamics of very special coarse-grained observables of the full theory, whose dynamics should be looked for in a similarly coarse-grained description of the underlying microscopic dynamics. So because you can see cosmology as the restriction of consideration to few macroscopic observables of global nature, probably close to equilibrium, otherwise you don't expect this restriction to be interesting, and to a large extent insensitive to the microstructure of the underlying quantum gravity theory, because it seems that effective field theory is a very good description of it to a good approximation. Well, then this suggests that cosmology has to be looked for indeed in the hydrodynamic regime of the underlying quantum theory of gravity. So this is what I'm going to do. Let me skip this. So we look for a simplest mean field description of the hydrodynamics of the group field theory that defines some interesting quantum gravity model. Interesting from the point of view of simplicial gravity path integrals, meaning that it seems that it has all the right discrete gravity degrees of freedom. This is the general rationale for what we're going to do. So the guiding idea is the following, that we need to consider a continuum phase which corresponds to a condensate phase of the original quantum theory, the underlying group field theory model we care about, that the relevant approximation is the hydrodynamic approximation, and then the point is that we have to first extract the hydrodynamic equations from the underlying quantum dynamics, then turn them into effective equations for coarse-grained geometric observables, and describe their evolution in terms of some relational dynamics, so with respect to some internal clock. So we start with the simplest approximation and then we try to improve. So let's flash you what the basic results of this approach are. Indeed, it can be shown that the simplest type of quantum gravity condensates, of group field theory condensates, which are basically coherent states for the field, allow you to immediately obtain a mean field description that involves an infinite number of underlying degrees of freedom, but they're all captured by a single wave function, as as you would expect in a mean field approximation. The nice thing, which confirms that the procedure up to now at least makes sense, is that if you look at the wave function characterizing condensates, which is basically the fluid density, you look at its domain of definition, so it's a function over some domain, and you can indeed show that the domain is isomorphic to the mini superspace of homogeneous geometries. So it's exactly the sort of configuration space for cosmology, for homogeneous cosmology. Next, you can use these states, plug them in the fundamental dynamics, and as you do in standard superfluids, you extract the effective dynamics, which is indeed the mean field approximation to the full quantum dynamics. That is, the classical equations of motion of the underlying field theory. Again, these are classical equations of motion for the field theory generating the sum over lattices and discrete path integrals. So it still accounts for an infinity of those discrete degrees of freedom in a coarse-grained language. For this particular class of states, you obtain the simplest hydrodynamic equation, which is the analog for the field theories we considered of the Gross-Pitesky hydrodynamics of superfluids. Now, the point is it's a nonlinear equation for the condensate wave function, which we've seen is like a wave function over homogeneous geometries. So this is like a nonlinear quantum cosmology equation. I hear strange sounds. Is it me or is it someone?
Well, I think it's my dog, sorry.
It's okay. I don't mind. If he has a question, I'm happy to answer.
Oh, sorry. I will try to eliminate.
Okay, so that's the second general point. And now I'm going to show you the results in one particular example, of course, skipping a bunch of details. But the point here, which is again general, is that indeed you can extract what looks like a nonlinear extension of quantum cosmology as an equation for the collective wave function for these condensates as the quantum gravity hydrodynamics. So the hydrodynamic approximation of the underlying group field theory. So I show you the results in 5 minutes for one specific model without giving you the details. So we take a specific group field theory model whose action written in the spin representation is the one you see in the slide, and it is extended to include not only the data that would describe in the lattice gravity level discretized geometries, but also an additional variable that, again, at the discrete level looks like a discretized free massless scalar field. But here we look at the description of the system at the hydrodynamic level, in which we simply have some condensate wave function, which is a function of the spins or group elements, and this additional real variable, understood as a real massless scalar field. We reduce to isotropic configuration, so everything is very simple, just a function of one spin and this additional real variable. We obtain the effective hydrodynamic equations. As I promised, I skipped all the actual derivation, but you get a nonlinear equation for such a wave function with parameters which basically characterize the underlying group field theory model you started from, this AJ, BJ, and WJ. So you see, it's a rather simple, after all, is a second order equation, but nonlinear in the condensate wave function. And again, if you think of it as a quantum cosmology equation, it would be like, for the first two terms, like a standard quantum cosmology equation, linear in the wave function, plus a nonlinear term. Now, we work now in the regime in which the interactions are subdominant, so they're just corrections to the free dynamics. We write down a bunch of observables in the full theory, so in the underlying Hilbert space, but we can compute them in the same mean field approximation, and they become just functions of the condensate wave function as well. the relevant observables for cosmology, isotropic and homogeneous, are just the volume of the universe at a fixed time. So this is again an operator computed in expectation value in the full Hilbert space, but on the particular states given by these condensate states, so that you can reduce to mean field. Then there is the momentum of the scalar field and the energy density of the scalar field. We compute them, and then we write down the equation of motion, that is the hydrodynamic equation for the theory. We rewrite it as an equation for the volume. These are two equations, and you can see that they are indeed generalized Friedmann equations in the following sense. First of all, the moment you go to the approximation in which, to simplify, the volume grows larger, then the equations reduce under an appropriate identification of the microscopic degrees of freedom to the classical Friedmann equations written in a relational language. So the Friedmann equation for the volume evolving with respect to the scalar field. So you get the correct classical limit, at least in this very simple case. And then the other nice thing is that quite generically, you can check that the volume never vanishes, and it has a single turning point through the evolution. So what you get is rather generically a quantum bounce replacing the Big Bang singularity. And this is just encoded in these equations of motion. Okay, then I just say that there are a number of results obtained to improve the old formalism, the approximations we used, extending the results and so on, and I'm not going to discuss them. I'm very happy to answer questions or to point to the literature. And I will use 2 more minutes to discuss briefly in this context, given what we learned so far, and in the perspective in which cosmological dynamics emerges as a sort of aerodynamics of the underlying quantum theory of gravity in this generalized lattice path integral formulation in a quantum field theory language. What happens to cosmological singularities? What do we learn? What can we expect? So we have seen, I just said it, that we have shown that the classical cosmological singularity is replaced by a sort of a big bounce scenario. And this can be seen looking at the equations, the effective equations I've shown, as a sort of a quantum gravitational pressure becoming dominant close to the would-be classical singularity and producing the bounce. This is very similar to what has been obtained in quantum cosmology, but now here we have obtained it within the full formulation of quantum gravity. Of course, one candidate formulation under a bunch of approximations. In fact, what I want to emphasize is that this result is general within the following restriction of the full theory. First of all, we had a mean field restriction. Second, that was a special mean field sector of the hydrodynamic approximation we took. And then we assumed we were in a condensate phase. So this suggests what limitations should be seen for this big bounce scenario within full quantum gravity. In particular, if the mean field approximation is improved, but the bouncing scenario remains stable, and a modification of the dynamics that coming from improved description of the condensate aerodynamics, then yes, then we will have shown that there is a cosmic quantum bounce even beyond the mean field. That would be remarkable. On the other hand, they would still mean that this is still under the condition that the hydrodynamic approximation holds, and that the quantum space-time system, the underlying quantum system, stays within the condensate phase. If it doesn't, well, if the hydrodynamic approximation breaks down, and it can break down for a lot of reasons. For example, that because fluctuations of the underlying discrete degrees of freedom become too big, quantum or thermal or other type of fluctuations, then what you're going to see is not a big bounce, but a breakdown of the very approximation in which you could describe things in terms of a continuum space-time. So what you would find what I would call a disappearance of continuum space-time. And this is not the result of numerical work. This is just the pictorial representation of the idea. If something even more drastic happens, meaning not only the aerodynamic approximation breaks down, but the reason why it breaks down is that the system is approaching a phase transition and leaving the condensate phase in which we had derived the aerodynamic approximation in the first place, then I would say we would be facing an even more radical disappearance of continuum space-time. And we need to describe what goes on in the very, very early universe and replaces the classical singularity in terms of some non-spatiotemporal description, really in the language of the microscopic quantum atoms of space, so to speak. So that's basically the last thing I wanted to say. And then I just remark that these three scenarios for the replacement of a cosmological singularity are in fact how to say, they can all be studied in detail, so they're not just conceptual scenarios that you leave as such. You can test the regimes of validity and the steps that bring from one to the other within this broader field theoretic reformulation of lattice gravity path integrals. And more specifically in the context of this group field theory condensate cosmology, using the quantum field theory techniques and methods from quantum many-body systems. So this is just to close, repeating what I said towards the beginning, which is that one good point about one advantage of embedding the lattice gravity path integral formulation of quantum gravity in this quantum field theory language, in this broader framework, is indeed that it provides new techniques that in particular allow to ask these questions in very concrete terms. Thank you.
Well, thank you, Daniela. I think we have time to ask questions. I'm sorry, I do not see here on my iPhone who is asking the question, so I need your help maybe.
I will tell you.
To tell me. So, do you have what other questions?
For now, there's no. There's one question from Daniel.
Yes, do you expect maybe some signature change in the early universe time, like around the geometrogenesis? There are several models which include like...
No, of course I know the loop quantum cosmology models, for example, where that is realized. So I certainly expect that the moment you improve in a number of ways that I can imagine, the simplest approximation we used so far to derive what is basically an effective quantum cosmology equation, and we get the modifications, then yes, indeed, there could be modifications closer to the quantum regime that could be understood as signature change in a very similar manner than in loop quantum cosmology. But at the moment, I don't have indications that would say that this type of modifications are more likely than modification that simply amount to breakdown of the hydrodynamic approximation or something else, because we haven't checked.
And some kind of dimensional reduction when you get really close to this.
So dimensional reduction. So dimension reduction is something we have we have hints, not only, of course, as you know, in a number of these approaches like dynamical triangulations and so on, but indeed we also had some work in which we shown dimension reduction for a class of superpositions of spin networks, which would be the type of quantum gravity states that we are coarse-graining in this description. So yes, I mean, dimension reduction could be another effect that we will see once we improve, taking into account more quantum effects, our effective cosmological dynamics.
Thank you.
But what I want to say just that we haven't seen it yet at this cosmological level. We have other indications in terms of the microscopic quantum states that is indeed an interesting possibility.
Thank you.
May I ask you the question too? Is it possible to go beyond this homogeneous space in this hydrodynamic approach? And what do you get eventually?
So we have done so far. There are well, a handful of works, maybe 3, 4, 5 papers in which we improve the description, and you can do it in several ways. You can go and study cosmological perturbations, but in the language of effective field theory, just taking from the full quantum gravity theory and modified background dynamics and check what the effects are. You find consistency with the rest of the formulas, but it's not a full derivation. Then we have indeed generalized exactly this mean field description to include inhomogeneities and inhomogeneous observables. And okay, depending how optimistic I wake up, then we have very nice indications of some general scale invariance in the power spectrum. But again, the approximations we use are very strong for deriving the spectrum. So we need more work to see if that is robust. But there's no, I mean, so to answer your question, the short answer is yes, of course, you need to be able to describe inhomogeneous observables in the same different variant language. So normally you need additional degrees of freedom to play the role of rods to define a notion of locality. You can do that. We have done it. So the kinematical setup is there, and we have some interesting results concerning the spectrum of inhomogeneities, but we are really at the beginning.
Okay, thank you very much.
Julian has also a question.
Maybe we have time for last question from Julien Grand.
Yeah, hi Daniele. So it was basically the question you had about inhomogeneities, but just to continue on this is so then how you will, I understood that then inhomogeneities is not in terms of scales, of length scales. So how you can relate these homogeneities in your framework to the more standard length scales we have in cosmology? I mean, yes, in classical cosmology.
Yeah, so the procedure would be basically the same you would have in loop quantum cosmology, because the end result of adding, rods, internal degrees of freedom that play the role of rods to have a notional locality, is that you're going to have some wave function satisfying here a nonlinear equation, because it's really the hydrodynamic fluid density, but it's a function over the space of homogeneous geometry plus 4 scalar fields, for example, some additional degrees of freedom, 1 being the clock and 3 being the rods. And the metric is what is in the quantum geometric data, and that gives you, dynamical distances and so on. And the other 3 degrees of freedom give you a notion of point, of a point in space and local regions. And then you proceed as you would do in quantum cosmology, generalized to the inhomogeneous case, to construct observables so that, for example, the volume density at a given point, the correlation between 2 volume densities at 2 different points, and all things like this. And they will come with the additional dependence on the quantum geometry. Okay. So the geometry will be dynamical. And so this is exactly what we've done in a first step, and we need to improve in the same direction.
Okay, thanks.
Okay, well, I think this maybe will let us thank the speaker again. Thank you very much.